Okay, now that we've gone over how to write net ionic formats of the chemical equation, I've got a sample problem for you here. Write the molecular, total ionic, and net ionic equation of sulfuric acid reacting with calcium hydroxide in an acid-base neutralization reaction. In order to be able to do this, you have to be able to write the correct formulas for sulfuric acid and for calcium hydroxide as your reagents, then be able to predict what the products should be in an acid-base neutralization reaction, then balance that equation, determine the correct state indicators of the products as we did up here, and then go through these steps of writing the total ionic and net ionic formats. So there's a lot of information that you have to have mastered in order to be able to do a problem like this. I would like for you to pause the video, and while you have the video paused, if you feel super confident about being able to do all of it right now, you can do that when you pause the video. All right, pause the video and please do that now. All right, coming back from pausing the video, we're going to write, the first stage is we have to write a correct molecular format of this equation. So that's what I'm going to do first. So I'm going to write molecular format, just so I know what I'm dealing with here. I've got sulfuric acid. Sulfuric acid, and ic acid came from an ATE anion. So this must have come from the sulfate anion. I know sulfate is SO4 with a 2- charge. That 2- charge means I must have had 2 hydrogens. So there's sulfuric acid, and of course, sulfuric acid is going to be aqueous. So I'm starting with sulfuric acid, and I'm reacting with calcium hydroxide. So calcium has a 2+ charge, hydroxide has a 1-. So I'm going to need 2 hydroxides to balance that calcium's 2+ charge. And that is a base. We can see it has the hydroxide, and there's our acid, so we can see that this definitely is an acid-base reaction. This is going to be aqueous, and we could look that up on our solubility tables. Okay, now I'm going to react an acid and a base, and remember that this is a special kind of double replacement reaction, where the hydrogen cations from the acid are going to pair up with the hydroxide anions from the base to form water. And for acid-base reactions where water is formed, I'm going to write water like this. Instead of H2O, I can write it like this. And by writing it like this, it will allow me later to balance these hydrogens from the acid and the OHs in water from the base as separate species, even though they are not really separated. So I've got water, and then the calcium is going to go with the sulfate. Calcium is a 2+, sulfate is a 2-, and so I just need 1 of each. Those are the correct formulas. We know that this is H2O, but I'm allowing you to write it as HOH in these acid-base reactions. That's okay. So we have water and calcium sulfate. Those are the correct formulas for our products. Let's balance the equation. 2 hydrogens from the acid, 1 hydrogen in water from the acid. So I need a 2 here. 2 hydrogens from the acid, 2 hydrogens in water. They came from the acid. 1 sulfate, 1 sulfate. 1 calcium, 1 calcium. 2 hydroxides from the base, 2 OHs in water that came from the base. So it looks like it's balanced. Let's get the correct state indicators. We know that H2O or HOH is going to be a liquid. It is not aqueous because it is not an ionic compound dissolved in water. It's a liquid. That's very important for this problem. For calcium sulfate, let's check its solubility. So if I look at my solubility tables, Rule 1, no. Rule 2, no. Rule 3, no. Rule 4, sulfate ions. They are generally soluble. Exceptions, calcium sulfate is an exception. So calcium sulfate is insoluble, so it gets a solid state indicator. Those are critically important to get right, because if I don't get those correct, then the rest of my work will be in error. So I have my molecular format of the equation. I'm going to move on. I'm going to write the total ionic. Remember that in the total ionic equation, everything that is aqueous up here is dissociated, unless it's a weak acid. So sulfuric acid, aqueous, it's not a weak acid, so I'm going to dissociate it. Now watch what I'm about to do. You see these two hydrogens right here? That is not an H2. That is not H2. Instead, it is two H plus ions. So how do I represent that? I say that I have two H plus ions. You see how those acidic hydrogens, you see how those hydrogens in the acid came down here as H pluses? And that subscript 2 says I have two of them, and so I'm going to use my coefficient to represent that. And they are aqueous. The sulfate ion is dissociated. Sulfate is a 2 minus. Notice every ion is getting its charge. Every species is getting its state indicator. So sulfuric acid is now dissociated into that. Next, I have a single calcium ion. Calcium is a 2 plus charge, and it's aqueous. Notice here I have two hydroxides. I'm not going to bring down the parentheses and the subscript 2. How do I represent that I have two hydroxide ions? I use a coefficient, 2 hydroxide ions. These hydroxides are no longer in a formula, and so I don't use the subscript to tell the reader that I have two of them. They are alone by themselves. So just as I did in the particulate or beaker diagrams, I use the coefficient to represent that I have more than one of them. And of course, they're aqueous as well. Everything on the reagent side has been dissociated because they were both aqueous, and neither was a weak acid. Now notice what's happening on the product side. There are no aqueous species on the product side, which means neither of these are going to be dissociated. So I bring them down just as is. So 2, I no longer need to represent it as HOH because I'm finished with balancing the equation. I know that I've got two of them, so I might as well just go ahead and write it as 2 waters, as 2 H2Os. I could write it like that, sure. But the only reason I wrote it like that was to help me balance it. And it's balanced now, so I know that I've got two of them there. And then I have a calcium sulfate. And there we go. So there's my total ionic form of the equation. Now, some of you may have caught already what's going to happen. You may have noticed that since neither of the products is aqueous, then neither of the products is dissociated. And what that means is that there are going to be no ions on the product side that are going to be canceled out with products on the reagent side, which means I'm not going to be able to cross out any spectator ions. If I can't cross out any spectator ions, then whatever is left over, and that is everything in this case, is brought down in the net ionic form of the equation. So again, there are no ions on the reagent side that can be crossed out with the same species on the product side. And so everything that was here just comes down as is. And this is the point at which a lot of folks will get a little bit, I'd say a little bit careless And they'll figure, I'm going to just write all this out, and they'll forget the charges on the ions. They'll forget the state indicators. I can't tell you how many times I have looked at an exam where all of this work has been done perfectly, and then students get in a rush to write this out at the end, and then they'll start leaving charges and state indicators off of these last few things, and so they don't get full credit for it. So be very careful about this. We don't want to make a transcription error when we have done such beautiful work up here. There's a sulfate. There's a calcium ion. Every ion alone by itself has to show its charge. And every species, ooh, I almost skipped it. Skipped a species after telling you not to do that. All right, 2 hydroxides, aqueous, 2 water molecules, liquid form, and a calcium sulfate. Okay, I'm just going to go through and check and make sure everything has a state indicator, state indicators, state indicators. I'm going to check to make sure every ion alone by itself has its charge. And there they are. Okay, it looks like I'm in good shape. Now I want to make sure that every time I had a coefficient up here, that I brought that down. 2, 1, 1, 2, 2, 1. All right, it looks good. And there is my net ionic equation. So what happened in this? Well, it looks like everything absolutely reacted. So when this acid found this base and they interacted in solution, the hydrogen cations from the acid, well, they were technically in the form of hydronium ions because they had been donated first to water to form H3O+. But anyway, they found the hydroxide ions of the base and formed water molecules. And similarly, the calcium ion found a sulfate ion in solution, and they also formed an insoluble species. So everything reacted. Moving on. We have another sample problem here. Sample problem B asks you to write the molecular, total ionic, and net ionic equations of sodium bromide reacting with barium acetate in a double replacement reaction. So I'll ask you to go ahead and pause the video and see if you can do the whole problem. And when you're done with that, restart the video, and then I'll work through the problem with you. Okay, coming back from pausing the video here, we're going to work through this. So we have a molecular format of the equation. So I'm going to do that first. It says sodium bromide, sodium +1, and bromide is a -1, so I need one of each. And that's going to be aqueous if we check our solubility rules. And then barium acetate. Barium is a 2+ cation. Acetate is -1, so I'm going to need 2 acetates. So parentheses, C2H3O2. That's one of a couple of different ways that I could write the acetate anion. As long as you have one of the approved ways of writing it, that's fine. And I need 2 of them, right? Because each of them is negatively charged, so I need 2 to balance out that +2 barium. That is also aqueous. So we have a double replacement reaction here. Double replacement reaction, the 2 cations switch places. So the sodium is now going to go with the acetate. Sodium is +1, acetate's -1, so I need 1 of each. There's 1 sodium cation, 1 acetate anion. And notice I do not use the parentheses on that acetate because I only have 1 of them there. If I look at my solubility tables, I will find that sodium is treated in Rule 1 and everything is soluble. And now barium is going to pair up with the bromide. Barium is +2, bromide is a -1. So I need 2 bromides to charge balance with that barium. Notice this is not a Br2 species. This is not a Br2 species. Instead, this is 2 Br minuses in that formula. If I look at my solubility rules, I will see that that is in fact soluble, so it also gets an aqueous state indicator. Let's balance the equation. 1 sodium, 1 sodium, 1 bromine, 2 bromines. Bromines are fixed. 2 sodiums, 1 sodium, 2 sodiums. 2 sodiums, 2 sodiums, 2 bromines, 2 bromines, 1 barium, 1 barium, 2 acetates, 2 acetates. And it looks like I have a completed and balanced molecular format of my equation with the correct state indicators. Okay, to save us a little bit of time, I've done some work down here, and I'm just going to cover it up and for now and reveal it as we discuss it. So we've just finished our molecular format of the equation. And some of you may have already noticed what's going to happen because we have everything up here, every species up here is aqueous. And none of these aqueous species is a weak acid. So that means all of these species are going to be dissociated in the next step. When we have our total ionic equation, every one of these species is going to be broken apart into dissociated ions. And the effect that that's going to have is it's going to allow me to cancel out all of the dissociated ions on both sides, which means I'm going to have nothing left to put into the net ionic equation. So this is a clue when we see it. When we see all of the reagents and the products are aqueous, we should start thinking, aha, maybe that means there's not actually going to be a reaction at all. So just to move things along, I've done the next step, and you can see that here I've taken my total ionic equation. Every one of these species has been broken apart into their ions, 2 sodium ions, 2 bromide ions, a barium ion, 2 acetate ions, 2 sodium ions, 2 acetate ions, and I ran out of space, so I just put them down here, a barium ion, and 2 bromides. Remember, this is not Br2, it's 2 bromides. So because everything was aqueous up here, I broke it apart into dissociated ions. And you can see what happens, that now everything can be crossed out. The bromides, the barium, and the 2 acetates can be crossed out. And that leaves nothing for the net ionic equation. So when I finally get down to the net ionic equation, everything has been crossed out and nothing can be brought down. What does this tell us? There's no reaction. When I added these 2 solutions together, the ions were dissociated in solution and they just remained that way. And so there was no actual chemical reaction. So this is just a reminder that I can have a few different situations. I can have a few different results when I have these net ionic equations. I can have everything reacting, in which case I'll have both of my products or all of my products will be solids, liquids, or gases, and therefore everything in my total ionic equation will come down to my net ionic equation. Or I can have some things reacting. Maybe one of these will be aqueous and the other won't be. So I'll have some things brought down here. And I can have a situation like this where nothing reacts. And just a reminder, what tells us that a single replacement reaction is going to take place? It's the activity series. What tells us that a double replacement reaction is going to take place? It's the net ionic equation. If you have a net ionic equation and there's nothing in there, then the reaction did not take place. So it's just to reflect again that we can write any sort of chemical reaction, but just because we can write it doesn't mean that it's actually going to take place.